we're going to be talking about the pigeonhole principle applied to the executive and assistant problem. It's probably the most challenging problem we've done in the pigeonhole series, but we'll be using the set function framework to help us, and we'll get started right away. So that's the setup. We have 15 executives and 5 assistants, and each executive gets one assistant, and no assistant is assigned to more than 4 executives. So obviously they're trying to make it so it's equitable, that an assistant doesn't get stuck with 10 of the executives, so they have a cap at 4. But even so, with this situation and the number of executives we have and assistants, we're still going to have at least 3 assistants are assigned to 3 or more executives. So let's do it. So let's first visualize our situation. That's our set X, that's our executives. So E1 through 15. And then we also have our assistants. And we know that each executive is assigned exactly 1 assistant, so that pretty much just means that there's a function, because functions have to use all of the inputs. And then no assistant is assigned to more than 4 executives. That's saying, in set notation speak, that's saying for all y in y, the size of all the pre-image sets is at most 4. So that's what that means right there. Okay. And we're going to do this via a suppose not, or kind of proof by contradiction. So we want to show this claim, and in order to do so, we're going to suppose that the opposite is true. So we suppose that it's not true that 3 assistants assigned to 3 or more executives. What does that really mean then? Well, that means that at most 2 assistants are assigned to 3 or more executives. Right, we had, it's not the case that 3 assistants are assigned to 3 or more executives. We have it that opposite must be true, that 2 assistants are assigned to 3 or more executives. So we just took this 3 and we made it at most 2. Because we're saying it is not the case that at least 3. That was our statement up here, at least 3. And so we took the at least 3 and makes it less than 3, and since we're with the integers, that means it's at most 2. Alright, so here's a little visual of what that means. That means we have an assistant here, let's say assistant 1 and assistant 2. And we know that these at most 2, so maybe 0, 1, or 2, but it could be 2, up to 2 assistants. Could have 3 or more executives assigned to them. So I'll put these little stick figures here. It could have 3 here or more. And also 3 here or more. And with those two bubbles, that's really saying that at most, so this is a version of the contrapositive of the pigeonhole principle, right? We're saying for each of these two y's in our assistant group, A1 and A2, for each of these, they have at most 3. So we go back here and we look, there's at most 3 that are in its group. And then as well, at most 3. Could be less. And so from that, we can say, from all this picture here and this sentence and this picture, we can say at most with those two assistants, at most 8 executives are served. All right. Furthermore, if we have those two assistants being used, we still have 3 more to go. So what can we say about the other 3 assistants? A3, A4, and A5. Well, if these two assistants, A1 and A2, are assigned to 3 or more executives, then the other 3 could have what? Well, we know we have our other 3 other 3 assistants here. And what can we say about their executives? Well, these blue ones, these blue assistants, are allowed to have 3 or more executives. So let's change the color here for these other 3. That means these 3 assistants that are different than the blue ones are not allowed to have 3 or more executives. They must have 2 or less. So that means we have 2 or less here. And same for A4 and same for A5. So 2 or less. And just as before, we can put another contrapositive version of the pigeonhole principle. So we have A3, A4, and A5. And back here in the executive set, we know that each of these 3 green assistants, they have at most, not 3 this time actually, my bad. They have at most 2 assistants that they're serving. Same here. Same here. So from these 3 assistants, at most 6 executives are served. And so hopefully now you see that a contradiction has arrived, because assuming not, we came to this at most 2 assistants are assigned to 3 or more executives. And we also got then that these 3 other assistants are assigned 2 or less executives each. And from that, we know that at most 8 executives are served from the blue ones, and at most 6 executives served from those 3 other assistants. In total, this would mean that the 5 assistants serve at most 14 executives. And why is that a contradiction though? That's a contradiction since we were told X was 15 executives. Therefore, our suppose not was incorrect, and therefore the original statement is correct, which means at least 3 assistants are assigned to 3 or more executives. And just recapping it all, remember we had a thing that we needed to claim here or need to prove. We said suppose not. From that suppose not, we went the negation of the gold statement. From that, we deduced that there'd be at most 2 assistants. Are assigned to 3 or more executives, which meant there's 3 more assistants left. So that means 3 assistants are left, and they are assigned to at most 2 executives. Because we're basically dividing up the assistants into those who can do or are assigned 3 or more executives, and those that are assigned, well, the opposite of that, which is 2 or less. And using the contrapositive of the pigeonhole principle, we said, okay, well, that means that this happens and that this happens. And so we have at most 8 plus 6 is 14 executives are served, and that's a contradiction overall, since we knew at the very beginning that we had 15 executives. And therefore, our original claim that we wanted to show is true. Hopefully that helps. That wraps up our pigeonhole principle section, and we're going to moving on to permutations and combinations next. See you then.